In this webcast, we're going to compare those two mechanistic pathways by which substitution at an sp3 carbon atom takes place, starting with that one-step mechanism, the SN2 pathway. Let's examine the transition state for that process. Since it's only one step in this mechanistic pathway, that step is going to determine the rate by which the reaction takes place. We'll call that the rate determining step. And in that transition state structure will be two molecules, the nucleophile coming together with the carbon atom bearing the sp3 center undergoing substitution. That's why we call it a bimolecular substitution reaction, because the transition state structure for the rate determining step involves two molecules. We'll take a close look at this reaction, which is an example of an SN2 process. The hydroxide nucleophile is attacking this sp3 center to end up making this alcohol and the corresponding bromide anion, which was the leaving group. We'll use these curved arrows in order to draw the transition state structure. The curved arrow on the left shows that there's a developing bond between the nucleophilic oxygen and the sp3 carbon, and so in the transition state structure we'll represent that bond, which is a partial bond, with dashed lines. The second arrow shows that there's a diminishing bond between the carbon and the bromine, and so in the transition state structure, that bond is also represented with dashed lines. Charge is an important part of the transition state structure. We see that there is initially a negative charge on oxygen, and then that negative charge transfers over to bromine, and so in the transition state structure, there is diminishing negative charge on oxygen and developing negative charge on bromine. The geometry of the transition state structure looks like this. It's called trigonal bipyramidal. The three groups that were not involved in bonding are in a common plane, and then there's an axis along the direction where the sigma star orbital is, with the incoming nucleophile and the outgoing leaving group that forms axis perpendicular to that plane. Let's take a look at an animation that describes the minimum energy pathway along which this reaction takes place. You'll find this reaction under the folder Elementary Reactions. It's the SN2 inversion of bromobutane with bromide. If we pull that up, it's going to loop through the process over and over again, and what you can pay attention to is the incoming nucleophile approaches the back side of the carbon with inversion of configuration as the outgoing leaving group leaves. For a second 3D view with curved arrows, I would suggest that you go to the ChemTube 3D site and check out the SN2 process. Here's an example of the SN1 mechanism, and immediately you can see that several steps are involved. The first step, the dissociation of the nucleophile step, is the slow step of the reaction. It's the bottleneck, the step that determines the overall rate by which the bromide is transformed into the alcohol. Since that step involves only a single molecule, it's a unimolecular process, and that's where the 1 comes from in the SN1 label. The dissociation step generates a very reactive carbocation intermediate with a low-lying LUMO, so low that it's able to react with even relatively weak nucleophiles like this neutral water molecule. When water combines with its lone pair on oxygen with the empty orbital on the carbocation, it's going to carry with it its two hydrogen atoms to generate this new carbon-oxygen bond, and still having the hydrogen atoms present. Since the positive charge was on carbon, it's now going to be on oxygen after this association of a nucleophile step. Every step in every reaction mechanism must maintain charge balance like you see here. The final step of the reaction is a proton transfer step, and it's going to generate our neutral alcohol. What happens in this proton transfer step is another molecule of water with its lone pair on oxygen removes the hydrogen that's on this intermediate. It's going to take that pair of electrons that is between the oxygen and hydrogen bond and return it to oxygen, so that the product will have a neutral oxygen, and the positive charge will now be on the oxygen of hydronium ion, which came from the base, water. We can compare the two substitution pathways on this reaction coordinate diagram. The one-step process, the SN2 reaction, has only a single barrier to cross, leading to the product. The SN1 reaction is going to have a very high barrier to cross initially that will generate this very reactive carbocation intermediate, followed by a low barrier in the association of the nucleophile step. In the upcoming webcast, we're going to find out which reactions will favor the SN1 and which will favor the SN2 pathway. In the meantime, go ahead and look at the ChemTube 3D site and compare the SN1 and SN2 processes.